Hello, this lesson is for Algebra 1. It's entitled Relations, and it's in Chapter 1, Section 6 of your textbook. And before we get started discussing relations, we have to go back and do a little bit of refresher and or teaching of ordered pairs. Sorry, my words got chopped off there. And to do that, we have to make sure that we understand the coordinate system. So what you have on the board right now is a diagram of the coordinate system. And when we refer to the whole system all at once, we generally call it the coordinate plane, which is what it says over here in the green. You should know that a coordinate plane or the coordinate system is made up of two number lines. And as you know, a number line has a 0 in the middle somewhere, and there's like positive numbers and negative numbers. And so what you have here in the black is the x-axis, or the horizontal axis, and it is a number line, where the middle here is x coordinate would be 0, and you have positive numbers going to the right, and negative numbers going to the left. You also have a y-axis, the vertical axis in blue here, and again, the middle being the origin, and you have positive numbers going up and negative numbers going down. A lot of times, you can confuse which is the x and which is the y, so it's the easiest to imagine the y-axis with a long tail, and if you do that, once you identify what the y-axis is, then obviously the latter would be the x-axis. So you don't have to remember it that way, but it's just a way that you might be able to remember it. So what do we use the coordinate plane for? We use ordered pairs, and we plot the ordered pairs onto the coordinate plane. So the ordered pair, I have a little definition or description of it over here. An ordered pair is basically where you list an x coordinate and a y coordinate together in parentheses with it separated by a comma. And it is important that this is not just any pair. It's an ordered pair, which means that the order in which you pair up the numbers does matter. And so we always want to put the x-coordinate first and the y-coordinate second. The x-coordinate helps us to describe left or right movement, and the y-coordinate helps us describe up or down movement depending on whether the number is positive or negative. In the case of the x-coordinate, if the number is negative, you would move to the left. If the number was positive, you'd move to the right. In the case of the y-coordinate, if the number was positive, you'd go up. If it was negative, you would go down. And so basically what an ordered pair does is it describes a location for us. So for example, we can do something like -2, 3. That's an ordered pair. And we can use this ordered pair to basically describe a location on the coordinate plane. And the way that we do that is we know that the coordinate plane, let me just come over here. We know that the x-coordinate goes first in the coordinate plane, and so since the first value in the ordered pair is -2, that means that that -2 is the x-coordinate spot, which tells us to go left or right. And as I mentioned earlier, the left means that we're going to go negative. The -2, sorry, means that we're going to go left. So we start here at the origin. This is where everybody starts their travels, if you will. And so we start here at the origin, and we move 1, 2 units to the left. And then because the y-coordinate is +3, we move up 1, 2, 3 units on the y-axis. And then we put our point there, and that would be the location for -2, 3. That would be where we would be, right about there. All right, so just, again, this could be a review for some of you, or maybe in some cases you weren't aware. So just want to make sure that we understand how to plot ordered pairs, because the definition for a relation is a set of ordered pairs. So you have to know what an ordered pair is in order to have a set of ordered pairs, in order to understand what a relation is. The other word that you see up here is the word set. And when you have a set, it means you have a collection of items. And in this particular case, we're collecting ordered pairs. When you have a set in mathematics, we typically enclose those sets, those items, in brackets. So you'll see here the brackets that we're using, the kind of funky looking little brackets. And inside there we have 4 ordered pairs, so a collection of ordered pairs. And that is our set. So this is a relation. And in example 1, they're asking us to express the relation as a table, a graph, and a mapping. Now you might know what a table is, you might even know what a graph is. Perhaps you don't know what a mapping is. And there is one other representation of a relation that is not up here, and that is an equation. We also can use an equation to represent a relation. But right now, we're going to concentrate on tables, graphs, and mappings. So for a table, that's probably the easiest one to do. We're going to make a t-table. We call this a t-table because, well, it looks like a t. And we're going to put the independent variable over here, x, and the dependent variable, y. And that's a whole other conversation we're going to have in a few minutes, but you want to make a column for the x and a column for the y. And all you want to do is place your ordered pairs one at a time into your table. So the x coordinate 2, the y coordinate 5. So you're going to put the 2 under the x column and the 5 under the y column. You do the exact same thing for -2 and 3, and for 5 and -2, and for -1 and -2. So that is your table. So we've done the table part. It's not very complicated. I didn't say it was going to be hard. I just wanted to make sure that you knew how to do that. And we also have to do a graph. So in a graph situation, we basically have to draw ourselves a coordinate plane like the one that we saw a little while ago. We'll have an x-axis and we'll have a y-axis. And so we'll have to plot each of these points. Okay, so I'm going to go ahead and just make 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It is important that you try to make your tick marks, I don't know what you call these little tick marks, pretty evenly spaced. You know, it's not going to work if you do something like 1, 2, 3, 4. In other words, the distance between 0 and 1 and 1 and 2 is very drastically different. You don't want to do things like that. You want to try, I mean, obviously it's not going to be perfect, but you want to try as much as possible to try to keep them as consistent as possible. So 1, 2, 3, and then you'll get better results that way. Okay, so there's my coordinate plane, and what I'm going to do is I'm going to describe, or I'm going to basically locate all of these 4 points. So 2, 5 is going to tell me to start at the origin and go 2 units to the right because it's a positive 2. I'm also going to go up 5 units because it's a positive 5. So 1, 2, 3, 4, 5. I place my point, and there is 2, 5. The next ordered pair is -2 and 3. So again, I start at the origin and I go -2 means I'm going to go, which we actually did -2, 3 earlier. So I'm going to start right here at the origin, and I'm going to go -1, -2 direction for the x, and then the y is up 1, 2, 3. My next ordered pair is 5, -2. The 5 again lefty righty. X-axis goes first, so we're going to go 1, 2, 3, 4, 5. And because of the -2, which is uppy downy, for the y, we're going to go down 1, down 2. And you can kind of see how it lines up with the -2. Our last ordered pair is -1, -2. So again, starting at the origin, go 1 unit to the left for the -1 and 2 units down for the -2. And put our point there. So now we have the table done, we have the graph done, and the last one is our mapping. And with our mapping, that's one of my favorites because you can be kind of creative if you'd like. I'm actually going to allow you to do that. Technically, all you need for your mapping is an open or hollow shape, kind of like that. This is your generic boring shape, but you can also make whatever kind of shape you'd like. You can make a star, you can make yourself maybe a big fat tree. As long as it's hollow on the inside and you can fit your numbers in there, you can make whatever shape you'd like here. I'm actually going to allow you to be a little creative in that regard. Okay? Not that the book is asking us to do that, but I just think it's kind of fun. But you just have to have 2 hollow shapes. They don't even have to be the same shape. Okay? And what you do in a mapping is you're basically going to kind of make a t-table. The only difference with the mapping is that we have to make sure that the numbers go into the mapping in chronological order. So as you can see for the x-axis over here, these numbers are not necessarily in any particular order. 2 does not come before -2, and so on and so forth. -2 does come before 5, but 5 doesn't come before -1. So these numbers should be in chronological order, and you should have no repetition. So you can see here that you have 2 -2's written down, which is totally okay in the case of the table, but that's not what you want for a mapping diagram. So in the case of the mapping diagram, you want the x variables or x values to be in chronological order. So we're going to say that -2 is the smallest number. The next biggest number would be -1. And then we would have +2. and then lastly, positive 5. Now they're what we call chronological order. You can see on the x-axis how it would go, -2, -1, and then +2, then +5. So they have to be in chronological order. Same is true for your y-coordinates. So the smallest y-coordinate is -2, and then we have a 3, and then a 5. Okay? So again, just want to remind you, you cannot have any repeated values. So even though the y has a -2 twice, we only put the -2 once in our little tree over there. So don't repeat any of the values in either column. And then also they have to be in chronological order. So those are two distinctions that we made for the mapping diagram that we don't have for the t-table. Okay, the next thing you want to do is what we call a mapping. So a mapping just basically kind of like a matching, if you will. We just have to go to each of the points. So here's the first one, 2, 5. So you just find your 2 over here in the x, because that's the x column, right? We have our x's and our y's. So you have to find your x, the 2, and here's the 2. And you have to draw an arrow from the x, from the value of the x in the ordered pair to the value of the y of the ordered pair. So this is 2, 5, so the 2 has to get mapped to 5. So the 2, we draw an arrow to the y, which is 5. So the ordered pair 2, 5 would be 2, 5. And there's your arrow. The next one is -2, 3, so I'm going to start with the -2 in the x and go to the +3 in the y. Draw my arrow. Now I have 5, -2, so there's my 5, and there's my -2 in the y. And then the last one is -1, -2. And that's your mapping. So the mapping's not hard either. You have to just draw the arrows that, from the x coordinate that corresponds to the y coordinate, just drawing arrows, kind of matching them, if you will. The only difference with the mapping that you have to be really careful about is that in the mapping case, you have to make sure that the numbers are in chronological order from top to bottom, and also that you don't repeat any values in the x or in the y. So if there's if there's 2 numbers in the y column, then you just write it once. The same thing would happen if it was in the x column. In our case, we didn't have any repeated values for x, but we did have repeated values for y, but we only write it once. After you've done that, you just draw the arrows to match up the ordered, or the x and y coordinates for each ordered pair. Okay, so the second part of this example is to determine the domain and the range of the relation. Well, if you've done a mapping diagram, then part B is very easy. So we're going to move this guy out of our way, and to get the domain and range, the domain is basically the x coordinates, and the range is the y coordinates. But like the mapping diagram, you don't want to repeat any extra values, and you don't want them to be out of order. So basically, if you've done your mapping diagram, all you have to do is recognize that the x part of your mapping diagram is the same as the domain. So we're going to put a big fat D for domain, semicolon there, and because it's a set, domain is a set of numbers, and the range is a set of numbers, we're going to put our funny little brackets, okay? And then for the domain, we want all the x coordinates, so we're going to list them. We're not going to put ordered pairs, we're just going to, so it's going to look kind of like this, but we're not going to have ordered pairs. We're going to have a collection of x coordinates, and the range is a collection of y coordinates. So, but again, they do have to be in chronological order, so we can follow the same arrangement that we have in our mapping diagram. Okay? We have -2, -1, 2, and 5 for our domain. For the range, we put a big fat R for range, and same thing, we want to put a collection of all the y coordinates, and we don't want to repeat anything, and we want it to be in chronological order. So -2, 3, and 5. And that would be our domain and range for this particular example. So there you go. Now we're going to have you try one on your own. There is your set, and again, they want a table, a graph, and a mapping diagram. And then after you're done with all that, you can determine what the domain and range are. Awesome. Okay, so the next thing that you're being asked to do is to identify independent and dependent variables for each relation. And before we get into the examples, I just want to remind you, when you think about independent versus dependent, independent means that, the way I like to remember it is I always think about our relationship with our parents. You know, we like to think sometimes that we're independent, but in reality we're not. We depend on our parents for everything. We depend on our parents for for food on the table. We depend on our parents for the clothes in our bag. We depend on our parents for permission to go somewhere. You know, when you want to go with your friends, you can't just be like, I'm going to leave. You have to ask your parents first. And if you don't, oh, I'm sure they're going to get really angry with you and probably frustrated with you. Maybe they'll ground you. I don't know. But you're not independent if you have to ask somebody for permission to do something. You are independent when you can answer or provide for yourself, and then you don't have to ask your parents for permission. So anyway, that's just one way that you can remember independent and dependent. So we're going to go through some examples right now and kind of try to identify the independent and dependent variables for the situation. Now remember that dependent means that you have to ask for permission, so to speak. So here we have example A. The dance committee is selling tickets to the fall ball. The more tickets that they sell, the greater the amount of money that they can make or that they can spend for decorations. So we've got basically, we have to do a couple things in this problem. One, we have to identify what the variables are. What are we talking about here? We're talking about selling tickets. Okay? So tickets is probably one of our variables. How many tickets are we going to sell? It says that the more tickets that they sell, okay, the more tickets that they sell, the greater amount of money that they can spend for decorations. So sounds to me like you have two things going on here. You sell tickets, you make some money, and depending on how much money you make, you can spend more money for decorations. If you only sell 2 tickets, you're not going to be able to spend that much money on decorations. If you sell 100 tickets, then you have more money to spend for decorations. So the question then remains, what depends on what? Do the tickets depend on the decorations, or do the decorations depend on how many tickets you sell? And I think that you'll agree that it's the latter that I just mentioned. The decorations depend on the tickets. The tickets are unaffected by the decorations. So we would say, in this case, that the independent variable would be our ticket sales. The ticket sales seem to be independent of the decorations. But the dependent variable in this case, to abbreviate, is decorations. Because our decorations depend on how much tickets we sold. Okay? So, next one, same thing. Generally, the average, why did I put that? I think I wrote that up there wrong. Generally, the average, we don't need this extra the, we have like an extra the in there, sorry. Generally, the average price of going to the movies has steadily increased over time. So, our variables are probably going to be time and price of going to the movies. So either the price of going to the movies depends on the time, or the time depends on the price. So which one is it? Well, I can tell you right now that when it comes to time, time is generally going to be the independent variable, because time does not ask for anything. Time just goes on whether we want it to or not. Sometimes we want more time in the day. Sometimes we want to pause our time and kind of wait, let me catch breath. And time just keeps on going. Time is independent, I would say 99.9% of the time. So for the independent variable here, independent, we're going to say time. Time does not ask anybody for nothing. It just keeps on going. Dependent, though, as the years go by, and I've felt this myself, it's so expensive to go to the movies now. Back in the day, you could go to the movie for $5. When I was in high school, $5 buckaroos. Not anymore. Now it's going to cost you like $15. It's so sad. So, dependent variable is the price. So we're going to give you a shot at this. We've got 2 examples here for you that you can try to determine, first of all, what the variables are. What are the 2 things that are being discussed in the example? And then secondly, which is independent and which is dependent. All right. Then we have our last example here. And this is probably going to be, hopefully not, but it could be the trickiest one, if you will. They're asking us to, we have a graph, and it says that the graph represents the distance that Francesca has ridden on her bike. Describe what happens in the graph. Now, a lot of times when I first put this diagram up, a lot of people, because they see that it's a bike ride, a lot of times people think that, you know, she's going up a hill, then the hill flattened out, and then she's going up another hill, But this hill is not as steep as that hill, because you can kind of tell that the steepness here is not as, the steepness here is greater than this steepness. So this hill must be the worst hill. But I can tell you right now, scratch all that, okay? Because that is not what this graph is about. It is very important when you read a graph that you definitely read the axes, the horizontal and the vertical. Here we have time, okay, which we said was, independent. And then we have over here, though, on the vertical axis, distance. Now, if this graph said time and maybe it said elevation, then it would make sense that this is how high she's going. It's the elevation. But this does not say elevation. It says distance, okay? This says distance, okay? Distance from how far is she from somewhere. So the thing that it's saying here, when you look at this point, this is the 0, 0 origin, remember? And the x-coordinate always goes first, so time always goes first. So when you think about 0 seconds, this person hasn't gone anywhere yet, because time hasn't started yet. And then the distance that this person is, for example, let's just suppose that Francesca is riding her bike and she's leaving from home. What this would indicate right here at the very corner is that she has not left home yet, because she's at 0, 0. She's at the time where she's starting, she hasn't started time yet. And the 0 here for distance means she hasn't gone anywhere yet, she hasn't left anywhere yet, okay? Now, if an hour later, here's like a 1, just pretend, if an hour later, this says 5, then this point right here would indicate that x would be 1 and y would be 5. That would mean that after 1 hour, if this is time measured in hours, then this would be 1 hour, she is 5 miles away from home. Or after 1 hour, she is 5 kilometers away from home, 5 yards, whatever the measurement is for distance, that's what that is saying, okay? So it's very important that you understand that when I say, what I'm saying from here and here, between this region here, is that she is riding her bike at a constant rate. Okay, because this is not fluctuating, it's very straight here. All it really means, and I'm like messing it up there, but all it really means is that she is riding her bike, and as she's getting farther and farther away from home. Because she used to be at 0, and now she's getting farther. The higher she goes up on this line, the farther away she is from home. So you can see that in this diagram, she's always getting farther away from home. Okay? Now what does this flat part mean? That means that, let's say this is like, let's call this, hour 2, maybe this is 1.5 hours, okay? So if this point represents 1 hour, 5 miles, then what does this point represent? That's 1.5 time-wise, but the distance from home is still 5. And at 2 hours, the distance from home is still 5. So for this entire lapse of time, she hasn't gotten farther away from home. She's still 5 miles from home. When you see a flat thing like that, that usually means that she stopped moving. So maybe she took a break. Maybe she wanted to stop riding her bike and she just sat down and started eating lunch. Or maybe she wanted to make a phone call. Or maybe she wanted to check her Facebook status. I don't know. But the point is she is not moving. So again, this indicates that she's moving at a constant rate. Here she's not going anywhere. And then here she starts moving again. But it would appear that because this incline is not as big as that one, is that maybe over here she's not riding her bike as fast anymore. She kind of slowed down a little bit. So anywho, that's kind of what's happening. So as a description of this graph, we have, as time increases, the distance increases until the graph becomes a horizontal line. So time is increasing, but the distance remains constant. At this section, Francesca has stopped. Then she continued to ride her bike. So they didn't even give as much detail as we did. We all talked about how the elevations here are different. So just be careful when you're reading these graphs that you are recognizing that what these things say on the side, because it does matter in your interpretation of what's going on. So we're going to give you a shot at describing what is happening in each of these graphs. Again, keep in mind that they tell you what the graph is of. So in part A, it's the person is driving to school. In part B, there's a change in income, so the graph represents change in income. And again, we have some steepness, some flat parts here. So make sure that you describe those, and we will talk about it in class and see what you did and what you got. Okay. So that was the last example for this lesson, and so once you've completed that, you will have completed your notes for today, and I will see you in class.